So, the following will provide 6G reminders. Let's see my work about WSH coding family. One feature is its encoder with double quasi-cyclic form. The DQC matrix provides its inverse matrix with the same form that is saving memory size of ROM for each parity matrix. Just store one vector and double circularly shift the vector to complete encoding flow. If compared with old techniques, the triangular matrix is too complex and not elegant. The length of WSH encoding is selected as a power of 2, which is convenient for the input binary number length. The parity of the WSH-ECC selects a fixed interval to match different power of 2 lengths and to meet the error rate of different input channels, finally forming a beautiful curve group. WSH-ECC is selected under stress tests. And following the hard decoding comparison, it will follow BCHT value over uncorrectable rate under 1 times 10 to the power of -8. All are done by hard decoding comparison, and are drawn curves again by 1-bit soft decoding. The implementation of the WSH coding family is based on the degree 4 parity matrix, which guarantees the simplest complexity for all modes in WSH coding. The QC size fixed by all modes is 64, 2 of power 6 that achieved 1 GBs encoding by x86 CPU. And the parallel processing of decoding could be 64, 128, or 192 bits that achieved over 100 Gbps throughput in 1 GHz clock. At most the hardware with 192 bits processing cost less than 650K logic gates. This is almost 40% off and quite efficient than any advanced system such as 5G. The noticeable difference is the decoder implemented by column shuffle architecture. In a mode-changing scheme, the decade ratio of throughput is proportional to the ratio of length, not parity size. It is easy if the system needs a hard scheme. If you want to know more details, please contact me. What is noticeable in 6G? A poor ECC will waste more time rescuing data, causing a huge gap between the system evaluation and the final result. A poor ECC will be more complicated and lead to difficult routing congestion and IR drop in the later stage. A better system needs design simplicity but not more adjustment methods. Following the 5G criteria is to build another 5G system. Please avoid a death spiral caused by poor design like 5G. The understanding of zero-knowledge proof is beneficial to 6G validation. We must think about how to discuss rationally and make accurate choices for high-speed 6G. At this time I would like to introduce a clearer formula to describe. The number of failures per unit time is equal to the system throughput times the probability of uncorrectable failures. The typical throughput brought into the application is 10 megabytes per second, if the vector of TXRX is roughly 1000 bits with volumes about 80,000 TXRX vectors sent and received per second. What is the difference between 1 times 10 to the power of -4 and 1 times 10 to the power of -7 of an uncorrectable failure rate? The former will have an uncorrectable event between 0.12 seconds, while the latter interval is about 120 seconds, 2 minutes. The viewers of the video can speculate that if we increase the transfer rate to 100 megabytes per second or 1000 megabytes per second, what is the interval between failure? At a speed of 1000 megabytes per second, the system requires a lower error rate than 1 times 10 to the power of -9, because the user does not want a shorter uncorrectable interval and often encounters failure events, affecting the latency by instability. What is the concept of testing 1 times 10 to the power of -4, 1 times 10 to the power of -7 until 1 times 10 to the power of -9? The error rate of 1 times 10 to the power of -4 is approximately 1 failure in 10,000 attempts. Out of 100,000 attempts, about 10 failed, maybe 7 or 8, maybe 12 or 13. Probably the designer has a foreknowledge that if the result is 1 times 10 to the power of -4, the test volume will probably be 30,000 to 200,000. This test volume depends on the designer's patience. With current computers, these attempts are about a minute or so, and this is a relatively simple cost. What about the estimated result of 1 times 10 to the power of -7? The difference is 1 times 10 cubed times, which is 1000 times. What is the 1 times 10 cubed concept? The cost of 1 minute of testing becomes 1000 minutes, about 16 hours. It is lucky to get the expected result after 16 hours. Please feel difference. Let me elaborate on this difference from 1 times 10 to the power of -4 to 1 times 10 to the power of -7. Oftentimes this is not the case. More of this testing process won't be done just once. If the result is worse, then the time lapse after the debug process has to be done again. It is very possible to change the setting, or it may be done again due to human misfortune. In addition, it may be that the expected result of 1 times 10 to the power of -7 is 1 times 10 to the power of -6, and the candidate needs to change the parity matrix again. Then it is necessary to try dozens and hundreds of matrix candidates one by one after testing and selecting. If a potentially suitable candidate is selected and the sensitivity to decoding is further tested with other settings, large error rate fluctuations due to reliance on unreasonable soft decoding may be uncovered. I was so sorry to say, discard this and move forward to test the next. After going through a full process, for a multi-length ECC family, you need to examine every ECC mode. Maybe parallel processing can speed up testing, but 20 or more sets of long-term simulations at the same time is tedious and tiring work. The ECC coding quality depends on the patience of the designer. Most players did it by lowering the verification criteria. When someone wants to improve quality verification, they are faced with the current market situation where bad money drives out good.